I get it. Okay. Blue sheets.
Do you want to go and do it?
Why don't you fill out one? I'll fill out one and then start. I can both start. This today. Today is the 17th. You need to put your name down first line to admit you were here.
Well, we put my name here.
Oh,
My name there as well.
yeah. It's a good idea. One of the things.
I can have a seat as well. That's a good idea.
All right. I'm most likely. Do we have a note taker? Okay. All right. Before we get started here, we need a note taker. I don't. Morning. Before we get started here, we need a note taker. Oh, the speakers work really well. I don't have to yell at the mic. Been too many Eat the Mic episodes this week. So we need somebody to take notes. We're just looking for brief notes. Don't need the blow by blow. Person A said X, person B said Y. Just a quick summary of what's going on, make decisions. Thank you very much, Stuart. And we can note one of the highlights from last night's Pekakucha is that Stuart is no longer the sole source of online Apple tech support. We really appreciate the fact that, seriously appreciate that Apple is sending more people.
So I'm Gory, and this is
David Black.
And Wes is somewhere, but not here. But available via email if you have a question. Maybe we start with a run through of the things we're going to cover.
Okay, so we're going to do a little bit of gender review and updates. We then have we have 3 SCTP drafts, one of which is an individual submission with some additional considerations for the UDP and CAP of SCTP, the L4S drafts. Then the highlight of your morning, we get to figure out what DSCP we want to use for the lower effort PHB for DiffServe. FEC frame update, and then we have 2 individual submissions, one on PMTU detection for datagram transports and an in-band QoS signaling draft. And let's see, we're also going to do something with the priority scheduler draft this morning, and that's getting done right now, almost immediately after we get done here. We're bashing agenda to do that fairly quickly. All righty. So, in addition, you want to do these?
One slide.
Just one slide. So, your secretariat and your work group chairs have been hard at work this week. We've been earning our exorbitant salaries, and here's the results. 2 new RFCs are out this week. 2 of the SCTP docs are now published as RFC 8260 and 8261. For recent experimentation, after a fair number of go-rounds, -08 version of this has been posted. Please review changes by middle of next week? Is that the 23rd of November? Yep. So please review things by the end of next week. The section on considerations for network consideration for ECN experimentation is the one that's gotten the most attention. So that could use a careful look at the text.
And since I'm document shepherd for that, just to be clear, this is past IESG last call. It includes all the text we expect to go in the finished RFC. So we're not really looking for review here. We're looking for, wow, this is right, or wow, this is wrong. So, but check it, please, because there's been many changes since it's in the working group. It's a very short time frame because we want to send it to the RFC editor as soon as we can. Fred next.
Fred, where's the? Oh, there it is. Alrighty.
Fred, would you like to step in the wonderful pink box? It's not very big here, I'm afraid. Do you want? Well, there's only 2 slides.
We'll answer for you.
Yeah, so in the Prague IETF, I was approached by a young lady by the name of Aeneas Finzi, who is finishing her PhD and has come up with a new scheduler. Oh.
That one you have.
Do I? Huh? I'm in the box. Okay, so at any rate, she has posted an internet draft describing this thing, and it contains some code that would describe at least a conceptual implementation of it. The idea is that she wants to make the management of elastic traffic a little bit more predictable than, say, AF or simple best effort schedulers might do. She uses the word AF to mean elastic, or the way we would describe elastic traffic. So there is some room for that in reading her draft. But so this is a picture of how the scheduler would work as traffic comes out of the queue. Then that changes the credit scheme. And now on the input side to the queue, traffic would be considered high priority or low priority depending on the state of the credit scheme. And the idea being to keep traffic fairly close to a certain boundary. So next slide, the other slide. Yeah, right. So in simulation, the thing on the left is how a standard AF scheduler would behave given increasing amount of traffic and a breakout of, I think she's got 3/4 of the traffic supposed to be AF or best effort, and 1/4 of it being expedited forwarding. And then on the right-hand side with her favorite scheduler, you can see that it is far closer to the exact breakout up to a certain point, and then it spreads as you would kind of expect it to do with the randomness of the arrival of traffic. So she's this is her PhD thesis, I guess, and she's looking for commentary on that. I think that would pretty much need to happen on the list because she's not here. So,
and actually, we can start here in the room, but also on the list. Chairs are looking for some input onto what is appropriate to do with this draft. First thing is figuring out whether people are interested. So please read this and comment on the list. And after that, we'll need to think about what we would want to do with this draft if people are interested. I mean, off the top of my head, it looks like, at the very least, some useful information for implementers.
So one of the things that I think about is, okay, how do we expect this to wander out into industry and actually be used? From a vendor perspective, vendors are going to put it into their chips or whatever. If vendors are coin operated, you send money, they do things, and so if you really like this idea and think that people would spend money to do it, then we can expect to see deployment. But I would expect that to come back from operational. This is something that helps us with making our business run. And absent that, I don't think it's going to see a whole lot of deployment. So especially if you have an operational viewpoint, I think that would be an interesting input on it. So with that, I think I'm done.
Yeah, please discuss this on the list. We've inherited AQM among other things, so this is the right place to discuss this draft.
And to reiterate, we're interested both in technical comments, level of interest, and suggestions as to what might be appropriate to do with this draft. Hang on a minute.
Next up, SCTP.
Now that I'm done scribbling. Okay, so I'm going to start with this one, right? Yeah, that one. Okay.
Hello,
Oh, Max.
Maxim Proshin. I will provide you updates on some SCTP drafts. First two drafts I will present on behalf of Michael Tuxon. Okay, the first draft is encapsulation of SCTP packets in UDP. Yeah, I mean, the title says about the scope of this draft. It applies to SCTP over UDP over IPv4 and IPv6. Doesn't apply for SCTP over DTLS. The main idea of the draft is to describe some problem that was found for RFC 6951, which actually describes encapsulation of SCTP packets. And as far as I remember, the problem is that that RFC requires verification, requires to validate verification tag, and for some SCTP chunks, verification tag is 0 or not available. So this draft basically describes the problem, and once it will be described, the draft will die, because then it will be RFC 6951 be created. Yeah, the status is that there are no any changes since last IETF. I think since some previous IETF meetings.
What would you like the working group to do with this draft? The default would be to just keep it on the agenda to remind people of the problem until a 6951 BIS draft is available. Okay.
That's what we agreed with Michael Tuxon.
Yeah.
Any ideas about timescales?
No.
Because you're not Michael Tuxon. Okay,
We have discussed it.
Michael's sending an email to me,
Yeah,
so that's
discuss it
on.
with him.
All right. Alrighty, what do we got? Next deck, I think. This one.
Yes, this is CTP network address translation support. Yeah, next slide. So yeah, the status is basically the same. There are no changes since last IETF. Michael still wants to reorder some text in the document, split up nuts and endpoints. and also describe translation from IPv6 to IPv4 and so on. I think he wants to update the example for IPv6.
Question, which might be for Michael. What's a good guesstimate for when this draft might be ready for working group last call?
Michael sent me an email.
Okay. We'll use that to invent a new milestone for it. Or rather, new milestone date.
Yeah, that's it for this.
Yeah, I'm sorry. I need to take some crucial notes for myself. All right, one more.
Yeah, the next one is more interesting, I would say. It's about RFC 4960 routing issues. Yeah, you know that RFC 4960 describes STTP protocol. And our work basically is to collect all the issues we have with that RFC and describe them one by one, so that, I mean, that will be informational RFC, and we will use it to provide RFC 4960bis. Yeah, right before this IETF meeting, we published revision 03, which includes remaining issues from our list. The first issue is about CRC calculation code. There is example in the RFC, and we agreed that it's not probably right to state short, long types, and we don't want this text be platform dependent, so we slightly updated it to use uint types. Then we also deprecated hostname parameter because it was never tested, I mean successfully tested. So our proposal is to clearly state that hostname parameter must not be provided during association negotiation, and that if it's provided by the peer side, then you should ignore it. Then we also removed some conflicting text regarding supported address types parameter. Yeah, and we also included some RFCs which update RFC 4960, 6096 chunk flux registry, 6335 about YANA procedures for port numbers, and 7053 for SAC immediate bit. Yeah, and then during this week we also discussed a few minor issues, few minor clarifications. That is why we published revision 04. And one issue is that we wanted to clarify that subsystem number is limited. I mean that you know that TSN can be wrapped around, and the RFC clearly states that you should not have more than 2 power 32 minus 1 SEN TSNs, and we added basically the same clarification for for SSN, so that to avoid any problems when SSN is wrapped around. And we also added some restrictions to GAP ACK block text in SAC chunk, because we realized that there might be some STTP implementations which don't follow the intention to have some break between cumulative ACK TSN and GAP ACK block. And that might be a reason for some problems from the sender side. So we clearly stated that there should be that GAP ACK blocks should be isolated, like it was in the TCP case. And then we also updated the reference to RFC 2119 by the other RFC reference. I don't remember exactly. Yeah, I mean, that is basically our work. We finished updating the document. We described all the issues we wanted to describe. The document is well structured. All issues are described in some specific form. The problem, what was the old text in RFC 4960, how we want to update the text. We don't have any open issues, and yeah, we always welcome to get comments, and we think that we are ready for our group last call.
Okay, so first item of fun. Could you raise your hand if you've read this or the previous version of the document? Okay, similar question. We need some reviewers for this document, which was my reason for asking the first question. We have already one volunteer from Kichung from Oracle for their stack. That's the Solaris stack, so that's cool. We don't have a volunteer currently to read Linux and check how that works. That would be fun if someone's willing to go and look at the Linux implementation. These people typically don't come to this meeting, so that would be really useful. And we just need other people to sign up to review this. We can't, the thing that's stopping us progressing this now is just lack of reviewers. So would anyone like to offer to review this draft? Yeah, can you go to the mic and tell me your name, please?
Peter Lay.
Yeah, thank you. Anyone else?
We'll also ask for viewers.
We're going to ask for reviewers on the list. If we can get people to sign up to review, we will start a working group last call.
Okay, good.
So heads up, this is heading for working group last call. If you will be willing to review it, please tell us on the list so we know that there's going to be enough feedback in working group last call. This is a relatively short document. If you're familiar with SCTP, it will be an easy read.
It's not a short document.
Wow.
It's like 80 pages.
Yeah, but it's
it's very simple because it's well structured.
Yeah.
Okay,
Okay, thank you, Max.
thank you.
L4S update is next.
Morning. I'm going to, L4S, when the BOF was set up, was decided it wouldn't be a separate working group. So I'm going to treat these sessions as a bit of a sort of cross-working group report on what's going on, as well as telling you what's going on with these drafts. So I'll first of all do a status update of everything and then talk about these drafts. I've stuffed a couple of recap slides in, but you can skip over these. These are just for people who don't normally come. The status of these two drafts, and there are three in TSVWG, but the architecture and the identifier are both really in a holding pattern, as I said last time, waiting for implementations, and there's some good news on that. I think on the following slide, it's this one. So status updates, source code is available. Open source code is very much as it has been. I've identified those things that have changed in red, and that is we've now got some implementations starting to come along. We have one in Silicon being started. I can't say when availability is going to be, but it's aimed at the data center environment. So it's the case where you've got existing, what you might call classic TCP traffic, and you want to move up to data center type data center TCP in the same data center like cloud. So it's for high performance switches. Then we've got one from our MCAT for real-time media streaming. got a implementation in Scream from Ingemar Johansson, which I'm going to talk about next. Then we've got an implementation of the whole L4S. That's the endpoint and the dual queue coupled AQM in NS3, written by Tom Henderson, who was one of the original authors of NS3. So that's going to be useful for people to do simulations, and that's been finished, but will be released early 2018, being tested now. Right, so I said I'd talk about this Scream implementation. Just some early results. This was actually completed on the plane here by Ingemar, and so we'll see more results later. This is with CODL, not with the dual queue, with one Scream flow running through it. One of these new Scream flows that can do L4S scalable congestion control. And the thing to look at here is the queuing delay. It's in the sort of 20, 30 millisecond range. This is a slow adapting real-time media. On the left, you've got the queuing delay measured network to network, network stack to network stack. And on the right, you've got queuing delay including, no, sorry, not including, the additional queuing delay in the application, in the RTP send queue. You can ignore the bottom for the sake of this presentation. That's the congestion window, bit rate, and things like that. So if you flick now to the next slide, you can see what the queuing delay is with L4S in the congestion control, in the Scream congestion control, and in the network. And you can see if you flick backwards and forwards, you've got significant difference in the network. You're down to not quite a millisecond, which we'd like, and which we're getting with TCP, but this is the first run with the new implementation, so hopefully we can get it down a bit, but it's certainly in the sort of under 10 in the 2, 3, 4 millisecond range with one spike. And that's what percentiles are for. Right. So let's move on. But that's good news. Starting to see implementations coming out. Regarding documents, this is the state of all the L4S drafts. Talked about the first two, which are in this working group. The dual queue I'm going to talk about next. ECN experimentation, David's talked about. Scalable TCP algorithm, we have DCTCP has gone to RFC. We can't use that directly. We can use it for trials in on the public internet, and in data centers we can use it directly. Accurate ECN is coming up, probably for working group last call in the...
Hey, Bob, what does RFC publish mean next to TCP Prague?
Oh, sorry, I didn't mean to write TCP Prague there. Sorry, that was editing a previous slide. That shouldn't say TCP Prague. That should be RFC published next to RFC 8257.
Which indeed is so, but it's not the same thing.
No, it didn't. Right. Sorry about that. Yep, accurate ECN I've just said. Generalized ECN, which is ECN++, has been updated a little, mainly to talk about experiments that have been done on traversal, which have found problems, and that was reported in TCPM, problems on mobile networks, but not problems in terms of anything drastic, just bleaching, which is benign but irritating. So ECN supporting Trill is still waiting for the chair to do the working group last call write-up. It passed working group last call. And design team formed for ECN in Quick yesterday, in fact. So everything's adopted except for that last one in Quick. And quite a lot is getting through fairly quickly. So we're moving nicely. 3GPP, Ingemar again tried to put in a proposal for putting ECN into the radio link control layer. That was rejected for release 15. Going to retry for release 16. Next.
Bob, quick question on 3GPP.
Yep.
And with luck, I'm not sideswiping people, what I'm about to say. My recollection is that Ingemar was trying to do two things at 3GPP. One was to get this in. The other, which was the predecessor, was to remove some problems. And there's Ingemar. He can explain what exactly what he was doing.
Yeah, maybe can you repeat the question? I didn't quite
Okay,
hear.
so my impression was this was part two of two parts, and there was an earlier work you'd done with 3GPP to take out some potentially problematic ECN language, and that was successful? Question?
I guess one of the things that sort of clarify the use of ECN, that was addressed more than a year ago.
Mhm.
The TS 36300 was updated because of that. And then we have the other one about the visibility in RAID link controller layer, and we're not there quite yet. So
Okay, sounds good. It was mostly wanting to give you a little bit of credit for past work. So thank you, sir.
Okay. Thank you. Next. All right. This slide is unchanged as regards papers, so move on. Oh, there's a URL there for all that I've just said on those last three slides at the end. That's the landing page for the project. Next. Hang on a minute. Right. David's going to show us something behind the curtain. No? Right. Okay. Dual queue coupled AQM. I've only got 10 minutes for this whole thing, so we'll move on. No, sorry, I didn't mean move on in that sense. Be careful what you say here, don't you? Right, so in the draft now we have a picture much like this has been added, and talk about the structure, which was sort of missing from it before. So those two people had have been trying to implement it, had read it, and found it difficult to understand because of that. So we now have an ASCII art looking like that in the document, although it doesn't look quite as good as that. One apparently minor change we've made to the structure is that little factor K there that you see in KP prime. That's the coupling factor across the middle there. We've shifted it. It used to be P squared at the bottom was divided by it. Now that might sound trivial, but it's it makes all the parameters, input parameters for the AQM independent of each other, so that you can change one without having to change others. And so we've had to go away from the original command line API of PIE to do that. But it's cleaner now. Next. So this is the same diagram highlighting the fact that the dual queue coupled AQM is not really an AQM. It's a framework for plugging AQMs into, and particularly plugging two AQMs. So you can see the two there, the L4S one and the base one. And the base one is used for both the classic and the coupling across to the L4S one. And in the appendix, you've got a couple of examples. And in fact, one of the implementations, the one in the high performance switches, is Kirby Red. The Pi squared I would recommend. It's a better one, but that proved, or Kirby Red proved easier for that particular implementation. And so that's nice. We've got implementations of two different AQMs now. And you can also put in different AQMs in the L4S one. We've currently got a step, but we're experimenting with a ramp. And the draft is structured in a similar way. It's the musts and shoulds are all about the framework, not about the AQMs themselves. Next. So the main thing we've added to the draft, other than the structure, is the management requirements, and splitting in that same structure the configuration of the framework and of each AQM, and what configuration parameters you're going to need in general for any AQM, as well as the specifics in the appendix. And then on the monitoring side of management, some advice on what you ought to measure. And this actually reflects, as you see in the gray box at the bottom, the Linux implementation, which we've restructured so it's classful, so the two queues inherit from the queue disk. And so you can get the monitoring stats for from each queue inside the queue disk, like you would get the monitoring stats of a single queue. And also use the in the Linux implementation, use the Linux classifier architecture so that you can add additional classifiers. And we've been talking with David and Gori about how that may be diffserv related, as well as address type classifiers as well. So that as well as the sort of hard-coded ECT1 classifier and CE classifier, you can put in additional classifiers on operator by operator choice. Right. Next. Oh.
I think. Well, David and I are both interested in knowing how it relates to DSCP. So that's really good feedback.
Yep.
And people want to ask questions at the end. That would be great on that.
So why don't we do this status slide, and then I can try to summarize what the early thinking is about what's going on here and what the goal, what the high level goal is. So Bob will have this slide, and then I'll try to say something intelligent.
Okay. So I wasn't going to say anything more about diffserv, but I can summarize our conversation if you want.
I was going to say, why don't you go up to this slide, hit the diffserv item last, and then we can use that as an excuse to talk about our conversation.
Yeah. Okay. Right. So thanks to Samini and Gaby. And what we're planning to do next is this came up in the ISG review of David's ECN experimentation, a request that anything about experiment should have the management requirements for the experiment. And
yeah, and the ops areas not only ask for management requirements, they're also asking for, actually, I think you may have this. I don't recall. They're also asking for something about how success or failure, or rather how outcome of the experiment will be evaluated.
Yeah. Now we have that in the draft, or in the experimental part of the draft. Yes. But I'd sort of already preempted this without realizing that this is what they were going to ask by putting the management requirements in, as if it was not an experiment, but just that's what I'd do, because you put something in the network, you have to have management requirements. But I hadn't thought about it particularly from an experimental point of view, so we'll do that next time as well, right? And I should add that some of the more recent changes to restructuring in the Linux implementation aren't yet available in the open sourced one, so we've got to release them. Already mentioned the relationship to diffserv, and we will continue to mention that. And we're also going to be adding queue protection policing discussion at some point. That's active work now. Thank you.
What I'm going to do is, so basically for the diffserv discussion, what I'm going to do is I'm going to put this back up, as that's as good a reference architecture slide as any for this discussion. So this is David Black speaking from the floor, and what I'm going to try to do is sort of give a preview of what's coming here, because we kind of sort of invented this on the fly this week. That's what IETF meetings are good for, coming up with clever new ideas with details to be worked out. The high-level goals, what's up on the screen there, is a dual queue structure. And as L4S was originally sort of put together, it was, okay, we're just going to have a pair of queues. L4S happens in one queue, everything else is in the other queue. The goal of what we talked about this week, and with luck will show up in some draft updates, is to enable multiple instances of this structure up there, so that the IPECN classifier could also be looking at DSCP and then send traffic into one of maybe two or three sets of dual queues, and maybe there's some traffic classes for which simply the L4S isn't turned on, and there's just one queue. Details TBD, as Bob I think pointed out in a previous slide. The Linux implementation can already do this by virtue of the fact that there's an upstream Linux classifier in general that's quite flexible.
Yeah, and that the Linux classifier fits in with either SDN or traditional command line type configuration, or MIBs or whatever.
Right.
Yeah.
And so just a heads up, and I will admit that I have a bit of enlightened self-interest here, and that after all the work I've done to free up ECT1, I'd like to make it usable a little bit longer term for things beyond L4S, as for example, we may learn a few things here, and we might want to have an L4S BIS at some point, and it might be good for them to be able to coexist.
But I mean, what I would emphasize though is the sort of point of L4S was that ultimately all your traffic, for at least for the public internet and for a lot of cases, could just be in the L4S queue, and the classic queue is just for old stuff.
Yep.
That will eventually, you know, after decades, disappear, and then you've got a low latency service for everything, and it's all simple, and you don't have all the complexity of managing diffserv and everything. But if an operator wants to have, you know, maybe in the interim, you know, a high importance class, they want to do emergency services or something like that, you know, then you've got the flexibility to fit it into the diffserv architecture.
Is it time for questions?
It is.
Okay. Michael Wetzel, just to get this, because now you're saying this is a framework that can run different AQMs. Is there a simple way of saying what the requirement is for an AQM in this framework?
That is actually what this draft is. You know, the body of the draft only says what the requirements for the for the AQM is in abstract,
right. So,
and then the appendix gives 2 examples. Yeah,
I thought so. I'm sorry.
Yeah.
I should have read it. Okay.
Yeah, so the musts and the shoulds, as it says there, are for the framework, and that means the coupling, the classifier, the scheduler, joining them back together again. Right, the bit that's grayed out in that diagram. Yeah.
Okay, thank you.
I think we're done.
Bob, when do you plan to update the draft?
Oh, it's sort of a continuous process, but
For the next meeting?
oh, certainly for the next meeting. Yeah.
Okay.
Yeah.
Thank you.
Right. Okay. Hang on. I can check to see what I've got Willem's one slide. He said slide. I think he did, but okay. We're getting organized for the DSCP Adventure LEPHB, and there was some just inside in time slide prep, and I got to go find that slide.
So, Roland, are you going to give us a update? Yeah, we have the slide.
Yeah, I found the
It'll be coming to a screen near you soon.
Okay, next slide. So yeah, that's the draft about the lower effort PHP, and basically what's left, as Gori already mentioned, is to fix the DSCP choice. And one important criteria is that other PHPs should not be marked to LE in case the upper bits are cleared. So the IP precedence bits are set to 0, then it should not actually be mapped to the LE code points. So the proposal was, after the measurements from Gori, to basically use a not DSCP, which are currently available for standards action. So the idea was to open pool 3 for of the DSCP code points for standards action. And if I understand David correctly, that would require short process document.
I will draft a short process document. The reason for having a short RFC to be about this is not really this draft, is to alert everybody else in the IETF that pool 3's changed its status, and that draft will simply change the status of pool 3. It will dictate the IANA rules for allocating in pool 3, and then in the meantime, your draft can be working group last called, and we can allocate from that.
Yeah, right.
And as part of that, we get to figure out whether it's DSCP1 or DSCP5. Those look like the two possibilities. Near as I can tell, it's a coin flip. When I flip my coin, it comes down 5.
I clicked it, came down to 1, but I mean,
Yeah,
like if
I'm also for
anybody
1,
has
but-
any idea whether 1 or 5 is better, you have a few months to do that. Just tell us.
Yeah, I'm also in favor of 1, but okay, that's personal taste. Yeah, so the draft needs at least one more revision, actually, to update to the new DSCP suggestion to remove this LE min, LE strict discussion. This is unnecessary, I think. And one thing that is left to or for discussion is I think I need to have a section on the update of the RC2B of 802.11. Right. So this is. So I don't know.
I'll ask David a question since he's here. Are we going to amend the Wi-Fi mappings? Now we've included this. I think we talked about this as a possibility when we working group last called the IEEE related document, and now's the chance to think about whether that's a good idea or not. What do you think, David?
I'm of two minds about this. In essence, I think this situation comes down, I mean, classic IETF mantra is rough consensus and running code. What you're looking at the slide here is some brand new bits not yet dry rough consensus, whereas the IEEE DiffServ draft is heavily grounded in running code. So off the top of my head, since I've just been asked and I have to make up the answer on the fly, I'm inclined to continue forward with the IEEE draft, with the mappings in it, because that's relatively stable stuff and reflects running code. And then we can figure out what we want to do to that draft as part of dealing with processing the LEPHB draft.
I think that's the correct position. So what we will be thinking about is how the other document will be published as is, and we're talking here about what we should say, first of all, about the new DSCP, and then whether CS1 should be changed, which I suspect we don't change because it's widely deployed. So this is the thing to be debated here.
Right. In addition, and showing my ignorance here, over on the wired side of IEEE 802, they actually do a CS1-like thing for less and best ever. Like, don't think Wi-Fi does that because it's a completely different scheme. Okay, Bob.
Well, Prisco, I was just going to suggest that you could maybe add an appendix that's, entitled "Upcoming Stuff" or something like that. Stuff to be aware of. And
that would be a good suggestion, because one of the things I don't want to do is we've spent an awful lot of time on that Wi-Fi draft, and I don't want to add another 6 months of waiting for us to clean this up to that draft.
That's not happening. We're not going. Yeah, carry on.
Andrew McGregor. Wi-Fi does have an LE-like queue, but what I'd suggest to do with the document is have this, when it is published, amend the Wi-Fi document.
That's what I'm kind of bubbling up to the top, and that would be my recommendation.
I think that was my point to update the existing 802.11 draft, but having my draft actually say that it will update this RC2B, right?
I think that's the correct thing to do, but that's a really good thing now to explicitly call out on the working group list, and we can get that sorted while we're sorting the code point.
Yeah, and still reviews appreciated.
Please use the list. Roland, can you send a very clear email asking these questions on the list?
Brian.
And Brian, something else?
Yeah. Are you going to say any more about the Pool 3 document that doesn't exist yet?
That'd be nice, yeah. Since I volunteered to write it, please comment on what will be coming.
I'll just, Brian Carpenter at the microphone. I just want to comment on that document. I think this is a perfectly legitimate thing to do, as long as it's properly done. I have very little sympathy with a domain which isn't checking DSCPs at its domain border, because they're the ones who'll be inconvenienced by this, if anybody is, but they're already in breach of the architecture. So my sympathies are limited. I just wanted to point this out. What it says in RFC 2474 about pool 3 is a pool of 16 code points, pool 3, which are initially available for experimental or local use, but which should be preferentially used for standardized assignments if pool 1 is ever exhausted.
Yes.
Now, you're changing that.
We are.
Because the pool is not exhausted. So you definitely have to do a formal standards track update 2474 to override that if statement. Otherwise, I think it's pretty straightforward, assuming you will leave it as a standards action pool, just like the pool 1 is a standards action pool. I think that will be fine. And as between 1 and 5, I don't know. My lucky number when I was a kid used to be 3. So I have that's the average of 1 and 5. So I actually don't care.
Okay, Brian, I have an additional question for you now you're at the mic. What you said makes perfect sense to me. This must be a PS that's published because it really updates things. Whether it's exhausted or not, we'll have to write text to say it's exhausted in the manner we wish to use it in, and therefore that's why we're doing it.
It's just wordsmithing.
It is. Thank you. That's what we seem to spend a lot of our time doing. There's another question which I've already kind of hinted at, which is pool 3's got many code points in. We currently only need 1. It looks like 1 and 5 both have similar properties, so it'd be really nice to have standards action for both. Do we now write a document that claims the whole of pool 3 and just changes the IANA action for that and makes it a standards assigned registry, or do we just reserve some code points in it?
I think it's a keep it simple, stupid case. I'd be tempted to just grab the whole pool because, all diff-serve code points are recommended. None of them are mandatory.
Yeah.
But because of the remarking at a domain boundary. So you aren't really breaking somebody's code by doing this unless they're not remarking at the boundary, in which case they're already outside spec.
That's helpful, and I think I would agree with this, unless somebody speaks up and tells us that's what we will do.
Yeah, when we see the draft, we'll tell you.
Yeah, I would agree also, particularly with the rationale that says anybody who's already using any pool 3 code points inside their network clearly is doing diff-serve classification and marking at the domain boundaries. Otherwise, they're doing something really stupid. We're not going to save them from themselves. And I think grabbing all of pool 3 is needed. We definitely need to take both code points, 1 and 5. LEPHB gets 1, and the other one has to go standards action because it's the only one that has the property that's usable when we care about IP precedence bleaching. Yep. And at that point, I think I'm inclined to be with everybody else here that says, "Oh heck, just take the whole pool."
Other people may comment if they wish. Otherwise, the action goes to me to write an internet draft with anyone who's willing to collaborate with me to get the words right. And then we'll present that in ops area, which will be the time when we may get feedback.
Right. And from the front of the room, with chair hat firmly on, a big thank you to Roland for his patience with this. This has taken much, much longer and gotten significantly more process complicated than what he originally signed up for to make this small fix. So thank you very much, Roland.
That's the end of the LE PHP fund for the moment and the LE code points. So we move on to looking at something completely different. We're looking at FECFrame now and the 2 drafts that we have as working group items in this area.
Okay, thank you, Jeff. Yes, I want to do a quick update on the first document and spend more time on the second one. So the first document is about an extension of FECFrame. Next slide, please. Thank you. So this is an already published RFC 6363. Goal is to add the capabilities of this FECFrame to also consider another type of FEC schemes for doing real-time flow protection, let's say simply. Next. So the situation is the following. We submitted the first individual document in July 2016. a little bit more than 1 year ago, and now we've reached point where it's almost ready. So I still have to review the document carefully and correct a few typos. Unfortunately, I didn't have time to do that for this IETF meeting, but already almost, well, the document in our point of view, myself and Ali Begen, the co-author, is almost ready for working with class call. So our plan is to do a quick update in December, maybe, and then if the group is ready, then we can continue the process with this last call. Well, that's for the document.
One quick note from here. Let's see, speaking as Shepherd, the intent would be to W working group last call both drafts at the same time.
Okay, no problem. We can wait a little bit. So the next one will take a little bit more time, but I guess that for next IETF, as I will say, as I will explain, it will be, well, close to the end as well. Okay, so this is the second document. This document is about a FEC scheme. That is to say, all you need to specify to be able to use a particular type of FEC within the FEC frame extended framework. So we made 3 main changes for this document. The first one is the addition of new co-author. In fact, Belkacem is working with me on the topic at INRIA, so he was naturally a potential co-author. Second change is about how we manage those FEC schemes. Initially, until the previous version of this document, there was a single FEC scheme, which means that this FEC scheme was for both the case where we have coefficients on finite field 2, on finite field 2 to the power 4, on the finite 2 to the power 8. I don't go into details, but it's simple math. So, well, it was one possibility, but we came up with this idea that it's not probably the best solution, because if you want to implement and provide a compatible FEC codec for this FEC scheme, you have to support all the 3 variants of coefficients, coding coefficients. It makes things a little bit more complex to implement, not that much, but a little bit more complex. And in fact, you won't be able to switch from one type to another type within the same FEC session. It makes no sense, because it will upset a little bit the decoding process. Once again, I don't want to go too much in details unless there are questions, but okay. So it was an incentive to, in fact, separate and have different FEC schemes, one for each type of mathematical process. So there is one for finite field 2, one for finite field, 2 to the power 8, and if we want, we can add more for finite field 2 to the power 4, or 2 to the power 6, or something else. So it's probably the best approach, we believe. Just one more note. In fact, if you look at the document, you will see that, okay, we specify the full scheme very carefully for finite field 2 to the power 8, and for finite field 2 to the power 2, it's just, well, it's almost empty. It's just a record, a new FEC encoding ID, a new identifier to say that, okay, this FEC scheme is for this finite field. You will have to use coefficients over this finite field, and everything else is empty. It refers to the related section for the other FEC scheme. So it's pretty simple in terms of writing within the document and specifying within the document a new FEC scheme. Next slide. So, okay, so the third change we made for this document is the following. We added an additional parameter, the ability to have a density parameter. So it means that initially we had equations where, well, just to remind you of the process, we have this sliding encoding window, and each time we want to reproduce a new repair symbol, we have to consider all the symbols within this sliding encoding window. We select a coefficient, we multiply each symbol by this coefficient, and we sum all the things. So it's simple math. The equation you have on top typically is the one we were supporting in previous version. All the equations were with non-zero coefficients. So each time you had to build a new repair symbol, you had to sum up all those source symbols, multiplying them by a certain coefficient. So what we want to do now is to be able to have sparse equations. Sparse equations means that a subset of those coefficients will be 0 So we ignore the associated source symbol during the encoding process and decoding process. Next slide, please. Thank you. So the motivation for doing this is the following. The encoding and decoding process with full density equations is a bit heavy. So it's not a problem when we are dealing with very small equations, let's say a few tens of symbols. This is something we can do very efficiently, even on lightweight platforms, even on a smartphone. I provided encoding decoding speed figures last time. So this is something which is quite easy. But as the equation grows, as you have encoding window of a few hundreds of symbols, then things tend to be quite computing intensive. So by reducing the density, you can increase the applicability of these fake schemes very easily. So this is the motivation for this change. So with the new approach, when you are dealing with small encoding, decoding windows, you do as you did before, no change, full density. And when you are moving to larger encoding and decoding windows, then you tend to reduce the density of those equations. Next. So as I said, we have a new parameter, this density threshold. This is a 4-bit field that is carried within each packet within this header. This is the red part of this header. You can see these 4 bits. This is not a big problem. If this density threshold, this parameter is 0, then you have the lowest density, which is in that case 1/16. So 1/16 coefficients will be non-zero. All the rest will be 0. And when you are using density value 15, then it means that all the coefficients will be non-zero. So it's pretty easy to address. We can carry that in each packet without increasing the overhead, transmission overhead. And this is also of course, an additional parameter that you will add to provide to the generate coding coefficient function. So it's quite easy to manage. Next. Thank you. Question, does it work? Yes, of course. It's pretty efficient in terms of encoding complexity. Of course, if you reduce by half the density, then you will experience an encoding speed multiplied almost by 2. Not exactly, we made quick experiments. It's not exactly multiplied by 2. In that case, it is plus 76% additional bit rate, but okay, it's efficient. At the decoder, it's less obvious. We experience some benefits, but we are quite disappointed by these 20% benefits. Well, it's really implementation dependent. We suspect this our decoder not to be fully optimized from this point of view, because this is an additional feature that was not supported before. So we still have some work to do on this aspect, but okay, we are confident that we can improve this a little bit. Next. Thank you. So now what we still have to do is to, do additional tests, making sure that really makes sense to add this additional parameter, and finalize the document. So I think that for next IETF, I will have a full figure, the full experiment ready, and the document will be close to the end, probably, most probably.
Okay.
Thank you.
Sounds good. Vincent, I have a small recommendation with chair hat off.
Yeah.
Let me go quickly back here. It looks like you've done the density parameter in the encoding as a linear encoding, where you effectively can encode code any fraction in 16ths, right?
Can you repeat? Sorry.
Okay, so it looks like the density parameter is the numerator of it's x over 16, correct?
Yeah.
Okay, let me suggest an exponential encoding where in essence the numerator is 1 and the density parameter tells you what the denominator is. That would give you 1/2, 1/4, 1/8, 1/16, giving a power of 2 every time.
Okay.
And maybe not exactly that, but that kind of idea will get you some more dynamic range that might be useful in the future.
Okay, thank you. Document? No. Okay, thank you.
So this is great work. Yeah, you can go. And It's the TSVWG covers quite a wide range of topics, and this is kind of in one area where maybe only some people have interest. But if you do have interest, please use the list. Please speak to Vincent, because this is a working group document. We'd love working group input to help Vincent get this in the best possible format, the best possible way, and progress this to hopefully a conclusion in London. Can I be Michael Tuxon? Can I be Michael Tuxon next? It's all right. Yeah, that's fine. You're taking this.
Oh, that one.
Yeah. Is that right?
That's what's next.
Okay. Hi, I'm Gori Fairhurst again. This time I'm... Oh, that's annoying. Is it? Okay, that's cool. Good. Spectacles are so annoying. I'm Gori Fairhurst, pretending to be Michael Tuxon. Michael's got a slightly different style, so I'll kind of pretend to be him. This is a draft written by 4 of us. We are trying to solve a problem that has been solved before. TCP has ways to discover the path MTU. Basically, there are 3 different ways in which TCP typically does that. It receives path to big messages from routers or routers that happen to send you these, and they happen to reach you. Sometimes that happens, and that tells you directly what the link MTU is along the path. We call that classical path MTU discovery. MSS clamping is widely used for TCP. It's a nice middle box technique if you have nice middle box techniques, because the middle box fixes the fact that maybe you have a tunnel or an obstruction along the path and the MTU is actually smaller than you thought, gives you direct feedback. And finally, these work quite well, but I'm not quite sure how the combination works, because we have a third method, which is path layer, path MTU discovery 4821. This uses TCP segments to probe that path, notified by these other mechanisms, and therefore to find out what actually works. The aim of this is to solve 2 problems. One is when your network finally evolves to be bigger than 1500 bytes of MTU space and we can send big packets. Well, we've got to do that sometime, guys. And the second one, when your network has a few headers that you didn't expect, and now the MTU size is smaller than 1500, which is often the case. So TCP has ways to do this. Next bit. No real way of doing this properly for UDP, because the first one works fine. Path MTU discovery works for UDP, except it's not as good as for TCP for various reasons, mainly because it's hard to verify whether the path to big messages are actually for the connection in UDP land that you're talking about, because UDP doesn't really have connections. Next one. There are actually many problems here, and many things that have to be different if we do this for UDP. Always black hole problems, and just read the draft and we'll go through more as we find those and fix them. What's a good path probe message for UDP? For TCP, we can send data segments, and if they don't get through, TCP will retransmit them. Hey, that's easy. Many UDP protocols don't really have retransmission of data segments, or not normal retransmission. They do some form of repair or something quite different. So the suggestion in this particular internet draft is we send padding packets, packets that have no value in terms of retransmission. They may be data that doesn't have to get through. They may be control packets, or they may just be completely null packets of the required length. What path MTU size should we choose? There's no MSS negotiation in a UDP session because there's no connection set up. So we have to choose a starting value for path MTU discovery. IPv6 is really helpful here because we have a starting value. So we can just use 1280 and hey, we know what should work and we can try it, and that works as a nice starting value. Other things, well, actually there's folklore in the internet about what might work with IPv4. and how IPv4 might give you blockages at different sizes. So we will have an effective starting point for a sensible probe. How do we react to a lost probe? Or even how do we detect a lost probe? So to make this work, we have to have a UDP protocol for which we can solicit an acknowledgement. UDP doesn't directly provide this, so this has to be provided by something on top of UDP. And finally, TCP, when it sends packets through the internet, keeps track of them and retransmits them for you. Therefore, you know when your current path MTU no longer works. For many UDP applications, we don't have a way of knowing that the current one didn't work. We simply send the data to /dev/null somewhere in the network, and that's kind of not the right thing to do. So that's a really bad black holing problem. So the solution to that would be simply to introduce these probe packets periodically when you need them, and they can check that it's currently working. So maybe we have some challenges here which we actually have potential solutions for. So, next slide. We could use this with a wide variety of protocols. If you use path layer MTU discovery, the path layer is the protocol that fits on top that does the transport functions. So TCP is a path layer, but so also are other protocol layers directly on top of UDP. SCTP over UDP, SCTP over DTLS. I put the SCTP in not to advocate SCTP, but simply because we do have running code currently in the BSD stack for FreeBSD that does this with SCTP for these two versions. So we're tweaking that and using that as a basis for development. UDP options, we currently have code running in FreeBSD that we are adding this to try that out with UDP options. And I'd say that these are reasonable strawmans for a sophisticated protocol like SCTP and a rather stupid protocol like the UDP options. And therefore, anything else that runs over UDP could also be added to this as other layers, other definitions. So we could add things for stun if anyone willing to work with us and figure out exactly how to do this. And we can add it for tunnel protocols if there was some way of generating the echo and other things you require. So hopefully it's going to be more generic and more useful than simply for these three things. Next. Aha, how does it work? Well, I mean, if you're sold perhaps on, hey, we need this, and perhaps there is a potential solution, what might that solution look like, and is it bizarrely complicated? Well, it's currently this complicated, with a whole list of hints about what sizes to choose. So let's see how this works. Next one. We start with no knowledge of anything and no intention to do path MTU discovery. Well, that's boring. Next. At some point, we've received an ACK from the other end, so we have the notion of a connection. Remember, it's UDP, so there's no real connection, just the path layer, path MTU discovery, which is rather long for an acronym. Algorithm has decided that it can connect to the other end. So it's time to check. So we start probing. We probe with a value we've guessed which works. 1280 for IPv6. Next slide. Then we keep increasing that probe because if that works, good, we can use the one that we guessed would work, and now we search for one bigger. We keep searching for one bigger according to a list of predefined suggestions until we reach the MTU of the sender. And if we know the MTU of the receiver, we use these both as a max to cap the probing. We probe until either we send lots of probes and they don't get through, lots being a number defined in the algorithm. We receive a path too big message and we believe it. We think we should authenticate that in some way, so that's part of this algorithm. How do you figure out the path too big message was really one that you can listen to? Some of them you can't because simply there is not enough quoted payload to know. In that case, that's really annoying. Other ones you can validate. The third thing is we reach the limit. Anyway, at some point we move over to the left. Yeah, we found the path MTU and we stay there because we discovered the effective path MTU and we can start using it. From time to time, this expires and we go back and we follow around and go and check again because that's what path MTU discovery does. And next. Supposing we get a path too big message or we suddenly discover that we're not connected, we may have to go below our recommended starting point and reduce the path MTU further. Okay, V6 is good because you don't have to reduce it much below 1280 because there's a minimum number in V6. Ooh, but V4, we can go right down to something crazy. So we have to have a way of going lower and figure this out. So that's what the probe error bit is, finding the lowest one that works and then rebooting the algorithm to work with that. And then, last, maybe we have to send probes all the time while we're in the state to prevent black holing, which was the scenario where all your packets go to /dev/null, and that's the loop at the bottom, which is it really still working with the current effective MTU that you're trying? So that's the algorithm. It's quite a few changes to the way in which TCP does it. And one of the things that's subtle, and the reason for is it really working, is because applications using UDP choose their own message size. So the packet size actually generated by the apps isn't necessarily the effective MTU chosen by this algorithm. And there needs to be a little interplay here just to make sure that it all works and you're not black holing half the data or anything crazy like this. So that bottom loop may be useful for many of the apps that want to use this. And of course, the apps can also say, please don't go bigger than this, because I have no intention ever of sending 64K or bigger segments. So just cap this at 2K or 4K or whatever number they want. Next slide. We have a draft. We have some recommended values, and we think this is a doable project. We have running code in the SCTP land and soon for UDP options, with some things to tweak. So if you're interested, please read the draft, comment on what we have or even what's not there. We have to decide at some time to tell the upper layer, that's the app in many cases, or whatever's sending using this, what effective MTU to use. That's not always obvious, so we're trying to figure out when you tell it this. How do we handle inconsistent results is a nice can of worms. There are many ways in which this can go wrong, and if we're designing something to be robust, it'd be really good to be robust. How do we handle a path to big message that's bigger than the link MTU or larger than the probe size? The answer is we try and ignore it. We find a good way to ignore it. How do we handle a path that's got forwarding inconsistency where sometimes we see one thing, sometimes we see another? Yeah, any bright people in the room want to help me out with this? This one I don't know, but I want a way of doing this. Dealing with middlebots that change packets. We're not going to go and blow them up or shoot them or anything, so we need to find ways to find out what sort of mangling happens. That might have to be some tests on the real internet to find out what goes wrong. And we really want to decide whether we're going to validate all path to big messages, because I don't want a method personally where people can inject path to big messages arbitrarily into this algorithm from any source and fake the source address and then inject me a path to big message that says forces a small MTU. So I think there's some security things here. I think that's doable as well. And next slide. Oh, what are we going to do? Well, clearly this is a work in progress. We have running code in SCTP. We revised the draft, so we're going to revise the code and check whether it matches the draft. The UDP options is a very simple change. It adds an echo field to a UDP packet using Joe Touch's work item, and that's really what we need to do it with UDP options. And we have that bit of code running, but we're now putting the MTU discovery part in. And we're interested in path MTU experience from people in general, because if this is going to be robust and elegant and actually work, we need to know where it will go wrong. Finally, no working group last chair on, but staring at David, we think this is useful work for TSVWG. So we'd like to know if this is the home and if it could be adopted, but maybe we should take questions first.
Yeah, let's do questions.
Michael Abrahamson. So I just want to comment on the usefulness. I can tell you I helped a friend of mine who had a video over UDP application with this exact problem 3 months ago. And he also had added problems that he had to handle the difference in the resulting packet size when he was, in his application was sending UDP over V4 and over V6. So he had to change, when he was actually handling the V6 things, that he had to actually take account for the larger header and all of that. So he came up with a very crude mechanism. It's less advanced than this. He just basically had 3 different values. If 1500 didn't, he like typed 500, 1000, 1280, and full size, and picked whatever came out of it. So I think this is very useful work. A related question: Do we know how many TCP hosts on the internet has PLMTUD turned on? I've never seen this actually being used, widely used. Do we have any numbers? Is there a document I can read? Do the TCP people have this? I don't know. Is this something we should? Is there someone interested in finding out? I don't know how you find that out.
I think you're in broadcast mode because we knew a lot about this. We know the path layer, path MTU code in TCP. We also don't know when it's called, and we probably don't know when it's turned on. We know it works in combination with the other mechanisms.
Yeah. So if there is a researcher room interested in figuring this out, it would be very interesting operational data to know if TCP speaking hosts like web servers and so on have PLMTUD turned on, because otherwise I think we should by now ask the operating system vendors to turn it on by default instead of having this as a knob that is default off.
Maxim Poroshin Eriksson. First of all, I support this work, and I agree that there are issues in this area. One question that I have is about your diagram, about some error state. I wonder, what do you propose to do with data packet that was already sent with wrong PMTU size?
Oh, that's easy to answer. We don't.
Okay.
So if your upper layer protocol, the PL in this case, does something like SCTP, then that protocol will take care of this.
Yeah, but
and it will have a repair method, and it will do something. This is a method that mimics something at the network layer, which is where PathMTU discovery belongs. So I don't believe it should be responsible for retransmission. So the only thing concerning retransmission is if the path layer knows, hey, I'm having these big packets aren't getting through, then it'd be good to tell us, but we don't handle that.
Yeah, but for SCTP it could be quite difficult because you already assigned TSN, and you cannot rebuild packet.
Yeah.
So I mean,
yeah. And speak to the SCTP people on our draft. And they have concerns about this, but there's nothing you can do, right?
Okay, do you have any list of issues somewhere in
at the back.
Somewhere?
At the back of the draft. In the comments field, we have currently a list of issues, and we have a Git thing as well, which is probably really what you asked for. So give me an email, I'll point you at the Git.
Okay, Vincent Rocard from INRIA. This is very interesting work and very useful, so I do support this initiative. It turns out that with a previous PhD student, we did some work in the domain of PathMTU and security, so I will have a few results to share with you.
Excellent.
So, thanks.
Yeah. Contributions really welcome. Thank you.
Hi, Bob Hinden. I support this work as well. I think we should have done this before. Have you looked at or thought about DNSSEC using this?
The reason I haven't thought about DNS, okay, so I thought about DNS because Alison Mankin said, oh, DNS needs to send big UDP packets and we don't really know how to do it properly. Have I thought about it? No, because I don't understand DNS. So if somebody understands the problem and they tell me it, then I may well be able to work for a solution.
Yeah, I mean, I think it's sort of the same problem, is that it wants to send big packets. And they get fragmented and don't get there and stuff like that. So this would be very helpful. But they also don't want to add a lot of overhead, why they don't usually run TCP. But that's about what I know.
Okay, all sounds interesting.
Michael Abrahamson again. So is this for the application developer who actually is doing the UDP application protocol? So this goes into that part, or is this an operating system thing?
There are 3 places where you can do this algorithm. The first place is if you believe UDP options is deployable, which we think it is, then you can put it in the stack and use UDP options to do that probing. It's the probe message which is the problem. Then it becomes a stack thing like path MTU discovery, except with the corner space of how do you handle the big packets that you want repaired somehow that will get black holed. But it will handle it for you, and you'll get occasional black holing of your data if you send too big. So that can be put in the stack. The second one is if you want to use SCTP or some other path layer that we design here, then you could simply add it as part of the transport algorithm. The third one is it's an algorithm. You can do it in anything over UDP. So if you want to add it to ICE or your favorite multicast app, then you can add the algorithm. The best, of course, would be UDP options if it widely works, because it's an operating system feature and you could just plug into it. 3 options.
Yeah, I think seeing the whole issue about V6 fragmented packets not being treated very nicely, it would be good if the application actually shrunk down its payload to go into each packet to avoid that. So I would prefer, and I know that'll mean less deployment, for this to be for the application developer itself, because then also if they put this into their protocol and sending their own application null frames, this means that you have the same 5-tuple, and there's less risk of these packets taking being hashed to a different path. So the whole inconsistent path you were talking about. Yeah. So I think all of the ones you were talking about is probably, I think they all have merit, but there are some cases where one of them. So I think we should have advice for all of these.
Right, okay. I'm kind of thinking that that's probably the only doable thing in the UDP space. Applications can be very different in UDP land, so you're always going to end up with the 3 options, I think. Spencer.
Spencer Dawkins, Transport Area Director on this one. Following on, I think what Bob was saying, the applications that have been at the application layer using really conservative datagram sizes because they want to make sure that it goes through everywhere. And even, the ones that even show up using the same MTU sizes on V6 because that was what it took for V4. It might be good if as this is going forward to be talking to the applications folks just to make sure that they can start thinking, watching this and saying, once this gets deployed, we've been saying for SIP specifically that, it kind of works, and it kind of works, and it kind of works. And one of these days we're going to be passing around keys and stuff like that in the signaling, and we're just going to be dead, but over a period of like a decade, people have been afraid, it's like, we're going to have to do something about this. We're going to have to do something about this. And I'm not quite sure why. I mean, it's like, it's obviously, this is obviously going to be bad. I'm not quite sure why it hasn't been worse. But just to be talking to major applications that people that are working in the UDP-based application space, and I think around here, I think SIP and DNS would be 2 interesting ones because they're both clamped to a small MTU size.
Okay. 2 other data points as my last words on this at the moment. The first one is we did present at Interia, and we got reasonably favorable feedback when we presented this IETF. And the second one is we do propose to go to the hackathon with our code next IETF and show that it works. So, David.
Hang on a minute. Well, let's see. So I think I heard 4 people come to the mic to actively support this, which is a strong expression of interest. Please raise your hand if you've read this draft. Ooh, okay. So we're going to be supporting this draft in principle. I'll go ahead and take the hum, but I think we're going to have to do the actual adoption call on the list. So hum if you think that TSVWG should adopt this draft. Hum if you think we should not. I heard a hum and silence in that order. We'll run the adoption call on the list and would ask people to please read this, particularly because of the level of interest being expressed in this work in principle, in some cases sight unseen.
Okay, we'll send a rev next week with the typos fixed. Sorry about the typos. So in the way of TSVWG, we have now a talk on something else completely different. So we're covering the whole of the transport area here. Yeah, that's fine. Yeah, I can do that. So this is a draft that's an individual draft. It hasn't been discussed a lot on this list. As many 0.0 drafts are not. So the purpose of this talk is to explain what is a fairly large framework. So once it's explained, you'll be more enabled to read the draft and pass comment on this and discuss this on the list. So please go ahead.
Yeah, this draft is was originally submitted to 6 men because it covered different areas, IPv6, and also working for transport. So they think that I have to get feedback from transport group. That's why I come here. Very likely this draft will be moved to either transport or new working group. So next page, please. So basically, why we come to the idea to do this? We want to do something for transport with on-demand quality of service. That's our fundamental. And why we do this? Because we think some application in the future that the current transport, which based on the best effort service, cannot support it. And think about MPTCP, because single session cannot get enough bandwidth, then we need to have multiple TCP to support bigger bandwidth. So we are thinking, taking another approach, that is to have a network device to involve more. Then also we want to have a granularity for QoS, which is fine than before. It can go to the flow level. Each TCP flow can have a QoS. And finally, to get the lesson from the history technology, we want our protocol very simple. So we have a design targets. First of all, it's a user or application can directly use that new service. And the second is the new service must coexist with the current transport technology, no matter if it's a TCP or IQM or ECN. They have to be backward compatible. Third one is that application can set up adaptive QoS, means that when TCP sessions established, the application can dynamically change such as the bandwidth without turn down the TCP session. Also, the first one is the service provider can manage the service to have a good business model. And the fifth one is that we want the performance and the scalability. It's for the new service are practical for vendor to achieve. So last one is for the network neutrality. We want this service to be transport agnostic, UDP or TCP, unicast or multicast can all use it. Next page, please. So here is our basic concept for doing this. So we want to introduce a new transport control layer in the IP, which can do 3 major functions. First one is the in-band signaling. It means that messaging can carry the TCP packet, but it's inside the IP header. That means even TCP is encrypted, we still can use it. So second is the QoS hardware programming information on path, IP path. So whatever you use for IP path, either shortest path or source routing, IP segment, segment routing, they can do this programming just on the path. Third one is that QoS programming state must be returned to the source. Then the source can make the adjustment or decision for the session. So second category is the congestion control. Because we have a network device evolved in the flow level control, then we can detect congestion state on the path. And also congestion state can return to the source. So third category is that path OAM. We want the path property be detectable and including the static property such as hop number and total bandwidth, also including dynamic such as the remained bandwidth or the queue size. So also we can want the diagnosis functions, of course. So for all this, our fundamental technology is to use the NPU for signaling processing and the QoS forwarding and the QoS state keeping. So basically right now, the current technology in the network processing is very powerful. It can not only do the normal forwarding and packet processing, it can also do some general CPU work. So the key part is that we store the QoS state inside the NPU, not the controller CPU, which can dramatically reduce the complexity of the protocol and increase the scalability. Because the controller CPU is involved as minimal as possible. So next page. So here is how it works in IPv6. So in IPv6, we use 2 extension header to do this. One is a hop-by-hop extension header to carry the signaling information. Second is that destination extension header to report the programming state to source. So by this way, we can have asymmetric IP path to do the QoS control. So for the hop-by-hop extension, even in theory, it will be checked by each hop, but we can configure the node, which we call it a hop-by-hop aware router. Those router can check the signaling message and process it. So this the selection of this router is really depends on the network traffic engineering. For example, if a router is a congestion point, normally it must be a hop-by-hop aware. And for the core router, for example, normally it doesn't have a congestion, then we don't need to do this. So the bottom map picture is a real network. We show some port which we must configure to be hop-by-hop aware. Next. This is a kind of experimental draft. So we do our experiment with our current products, which is a current access router, which is low and middle range. And with one NPU with traffic management module inside. So next page. This is a diagram of our packet forwarding. So fundamentally, the green line we call the DIP flow process is for the actual module we added for this purpose. So basically, whenever the packet come in, we will check the classification. If it's in the flow level QoS table, then we do the QoS process, then forwarding to the same interface as the IP forwarding. If it's not, then they go to the normal path. So next page. Because the QoS, the scheduling and the queuing is done by hardware. Here I just show the high level hierarchy of our queuing and the scheduling. So this level is more than normal Ethernet switch like Broadcom Trident. It has much more flexibility and power. But I checked other vendors' process. It's kind of similar, and so I believe other process can also do similar things. Basically, we have a couple level of queue, and each queue have either one or two scheduler. We support strict priority and deficit weight round robin. And also traffic shipping is for the dual or single leak bucket algorithm, which is our old technology, not very new. So basically this chip is supporting 64 gig, one chip. So next page. And here is the result. The above picture shows that we have a DIP flow first, the B1 and the B2, then we have a traditional TCP come in. We can see that traditional TCP come in doesn't impact the bandwidth of the new TCP. And the bottom picture shows that we have traditional TCP flows coming, then we have a new TCP coming, we call DIP. Then we can see that the new TCP will take over the bandwidth from the traditional TCP, which means we give the higher priorities to the new TCP. Because this is it's just a concept demonstration, we show that the network is in heavily congested status. Ingress rate is 4 gig, but egress only 100 meg. So next page. This is a latency picture. Top left one is the new TCP, and the right one is old TCP. The bottom one is two pictures merged together. So we can see that the probability for the new TCP can reach as low as 1 millisecond. But because of our measurement, we just make the queue pretty big to measure it, because we use a very old technology to measure user ping. So in theory, that real latency for the new TCP can be much lower than this. So we can see that just a separate two type of flows, we can obtain much better latency. Next page. So this is the most concerned part, scalability and the performance. For scalability, because at the beginning we designed this protocol for the applications that normal TCP cannot support, which means for normal TCP applications such as web browser, email, you don't need to use this technology. The application uses this technology only is that when they want very high bandwidth or very low latency. For example, if one NPU support 100 gig, then we divide 50% for the new TCP session. Then if each TCP session support 100 meg, then we only need to support 500. In our experimentals, our NPU can support about 1,000. So which means the scalability is not a problem, because in the real router, the NPU is kind of per port based, not per system like a control CPU. So for performance, in our testing, we measure it about 1 or 2 milliseconds per hop processing. When the signaling message come in, we need about 1 or 2 milliseconds. Let's assume it's a 10 milliseconds per hop. Then 32 hop, only 300 milliseconds. It's still acceptable for the new technology, because compared with ISVP, for example, it's much faster. Next. Here is the contents from here is not in the draft, because the draft is about the framework, not focusing the congestion control. But here, because this is a community, I just briefly introduce what we do for the congestion control for this regard. So even the network can provide some guaranteed service. It doesn't mean the congestion control is free, because normally the real implementation is that we guarantee the CRR. CRR is the commit information rate, but we don't guarantee the hardware resource for the PIR. That's a real normal implementation to make the utilization higher for the network resource. So if we guarantee CIR and not PIR, we still have to do some congestion control. So basically, for the congestion control, below is what the sender should do. We will measure the RTT, then calculate two windows. One is the minimum window, one is the maximum window, corresponding to CRR and PIR. Then we will choose the minimum one to be the effective window to send the data packet. This is the window we still have to use, but it's a different algorithm. Next. But for this rate control, we still have to change. So basically, for example, if you have a CRR there, you can start the traffic by CRR directly. You don't need to go to slow start. And we can take the same approach as TCP Reno to go higher and higher to the maximum window. Then we can see the pattern of the traffic will be still sawtooth, but it's between higher range. And also source can traffic either by window or by the passing to measure the rate, to send the rate according, different traffic rate according. And also congestion control is used for the forwarding packet lossing distinguishing, because right now packet lossing right now in the old algorithm is used for the detection of congestion. But with our hardware involvement, we can have a better distinguishing. For example, OEM can detect the remain bandwidth and the buffer depth and the buffer read threshold. And all those information can report to source. Then if a packet lost after OEM buffer read, which means it's really like caused by congestion, not by physical failure. Okay, so if a packet lost due to timeout, it's very likely caused by the physical failure, either link or network. So for the congestion and failure action, we have a lot of things to do. For example, congestion loss. We can have the same as the traditional TCP, the source can reduce the traffic, but it's not by half, but you can reduce directly to the minimum window. And if the packet loss is a random physical failure, then we don't need even to reduce the rate. This will dramatically improve the throughput. And if it is a physical failure loss, then source can reduce the window to 1. Means that network has some problem. I need to reset up my session. Reset up means that I will send this in-band signaling again to reprogram path, because the IP path may be changed. Then we have to send the data as minimum as possible. So this is a scenario of path repairing case. And if it's a forwarding failure, the source can reduce the window to 1 as well. So also resend the in-band signaling. Next page. Here is some high-level summary of guaranteed bandwidth service. So DIP flow, we call new TCP, and TCP flow share the same queue. And each DIP flow configures CIR and PIR. So the system will guarantee the resource for the summary of all CIR, as long as the CIR is sum is less than link bandwidth. So we have two scenario congestion. One is a DIP congestion, one is a TCP congestion. So basically, if no congestion, all DIP flow is guaranteed to obtain the minimum bandwidth of CIR. And the TCP behavior is the same as before, but the TCP bandwidth is the link bandwidth excluding the real bandwidth used by DIP. So when DIP is congested, then it's different. DIP only guarantees the CIR, means that each flow, as long as your your flow rate is less than the CIR, then you still guarantee. But above of it, it's depend on how much bandwidth remained and what is the algorithm used. We can have either the actual rate is proportional to its PIR, or the actual rate is distributed between all DIPs. Also, if a TCP congested, first of all, TCP congestion doesn't impact the DIP because the totally scheduling and queuing are totally separate. So TCP congestion only impact TCP flows. DIP still gets whatever they want. Next page. So for guaranteed latency service, it's a little bit complicated because guaranteed latency service, we have to think about the how many flows share the queue. So in our test with experiment, we still use all DIP flow share one or multiple high priority queue, and all TCP flow share the low priority queue. So the maximum latency can be easily calculated by the queue size or from the dynamic queue depth of the packets. So also we have two scenarios. One is no congestion and one is congestion. When the DIP congested, then the DIP queue will be built up. Then we can measure the latency based on the dynamic queue depth. And the TCP congestion doesn't impact DIP, so which means that no matter what, the DIP latency is still measurable. Next page. So this is as a summary. This is a framework of this new scheme to do the transport service with QoS. And this work is also part of ETSR NGP. It's called the Next Generation Protocol project. And it's still in process. It's not finished yet. I will keep update for this. Thank you.
Can I just ask a clarification question on the last slide? When is the NGP work likely to finish? Do you have an end date in mind?
You mean when it's finished?
Yeah. When do you expect that work in ETSI to complete?
Okay, so NGP has a couple of projects. It will last probably at least 1 or 2 years. It has started already for more than 1 year. So this working item, this is called working item, will finish by middle of next year.
And are there multiple proposals in ETSI NGP, or
Yes.
is this the?
Yeah, this is just one of it. We have about 10 working items. So this is the one working item.
Okay, thank you. Let's take questions from the working group.
Yeah, this is Roland Bliss, KIT. I see several problems with this approach. So usually signaling try to be simple has some problems with, let's say, at least security issues. So
Yes.
I don't actually know what the trust model is. I mean, I did a lot of work in ANSYS back in those days, but so I don't see how actually what you expect from the endpoints and how you trust the marking. And at least one functional thing that worries me is that you're not passing back the report message along the same way as you do the reservation request.
Yes.
So if you have, let's say, not enough resources, let's say you ask for,
Yes,
I don't
yes.
know, 8 megabit per second or so, but then you can't get that.
Yes.
And usually what you do is it gets decreased along the path. And so you have reserved resources at the beginning of the path, and you want to make them freed if you only could reserve, let's say, 4 megabit per second up to the end, right?
Yeah.
I don't see how that happens in your
Okay,
work,
so
right?
here we definitely we try to get rid of the complexity of ISVP. For example, the reservation. As I said, the reservation is that we keep only a fixed time of the life for the reservation. If no data packet come in, then the resource will be released. This is the first thing. Means that I don't need to come back to reserve like ISVP. So we only have programming one direction for one message. We don't need to come back. The come back just report all programming state. If the programming state is failed, then the source will decide if it will use the traditional TCP mode or reduce the bandwidth requirement. Because even some node has a reservation, but that reservation will be gone after no packet for a while.
Okay.
Yeah, this we have also for security. So we do have some simple security mechanism in the signaling, and we can guarantee that the signaling message is sent by authorized user. That's a basic security we can have.
I think I have to read the draft.
Yeah, draft has it. Yeah.
So I'm relaying for Michael Scharf, who said he wants to point towards RFC 6077, which describes many of the challenges that such a scheme has to solve in reality.
Yeah, I will read it.
Wolfgang Beck, Deutsche Telekom. I think there's a business model problem here because nobody would implement such a scheme without charging for the reservation, because you actually use up state in your network. And when you come to that, you fall under regulatory requirements. If you measure by time, you have to be very accurate, and then your network would have to have some timers to release the resources.
So the life is still not short. For example, we can set up 8 seconds for the reservation. If 8 seconds and no packet come in, then resource released. That's configurable.
Of course,
yeah.
If it has to work across multiple internet providers.
That's a different thing. In the draft, I mentioned that this is only for the one administration domain first. Multiple domain issue, we can go further to study because there's much more issues there.
And then, of course, you get all those issues. What if you have to reroute to a router which is not in the path?
As in the draft, I have detailed things for this. We call the path repair. For example, if rerouting happened or link failure or whatever failure, then our forwarding state will be failed, sent to source. Source will detect it. Then source will try to resend the signaling message, then to repair the path. The path will be re-established if the rerouting finish. Yeah, because all those things is in the documents. I didn't say details in the slides.
David Black speaking as an individual. I think you may have answered part of this question by saying that right now this is scoped to a single operator, single administrative domain, full stop.
Yes.
How does incremental deployment work? Can you deploy this incrementally, or does the operator have to enable this on every single router?
Definitely, in the draft, I list a couple of issues we have to study further. Multiple domain and heterogeneous network, all those things we can study further. But for multiple domain, definitely it can work. Think about the old TDM service or ATM service. That's a multiple domain issue. It works. So this one is simpler than that because this one doesn't involve any new protocol.
Wait a minute.
Routing protocol is not there.
Time out. Yeah. Time out. You and I clearly have very different ideas about what the word protocol means. I think I see 3 new protocols in here. So in essence, the question is, how is this going to behave if part of the network supports it and part of it doesn't?
Then the source will know this path doesn't support.
Okay, so I think you've got a walled garden system here, and I'm at pains to understand how this would get deployed on the internet in general.
Yeah, that's a much bigger issue because that's a lot of work has to be done. Yeah.
Hi, Lynn. Bob Briscoe. I read the draft, and I don't think you've addressed the question of buffers that are at layer 2, not layer 3. Or within tunnels and getting these signals to go up and down tunnels.
Yeah.
I mean, you know, there's a lot of other problems with this.
Yes.
But that's, I think, certainly from my experience of just getting 2 bits.
Yes.
To go.
So basically, those kind of things is related to the heterogeneous network through tunneling or L2 or MPS. Definitely, we need to have some interworking things for there. This one is just the first step, the framework for the pure IP network in one administrative domain. Yeah, I cannot cover a lot of other issues. Even this is more than 30 pages. So yeah, all those issues, we are thinking about it. Yeah, thank you.
So that's interesting, and it's good to hear about the NGP project. What are your intentions now with respect to your draft?
So first of all, as a reporter for the new transport technology in NGP, I like to share our progress with IETF because normally we have some liaison communication with IETF. Also for this is first step. We will see if this framework can be accepted in IETF.
You've heard feedback, and I think you have to now consider the feedback.
Yes, definitely.
Some of the feedback relates to security issues.
Yes,
they're obviously very important.
Yes.
You also heard feedback relation to operational ways in which IP protocols work.
Even business model is a big issue. I tell you, because this is a completely change for the current IP model. Yeah,
indeed.
Definitely. Yeah.
You also heard transport issues.
Yes, I didn't have a separate draft for that. In the slides, content is not in the draft. Draft is a high-level framework. Yes. Maybe the congestion can be different. Yes.
I think the congestion control model you have is quite different to what the IETF normally uses, except when they're using a reservation protocol.
Yeah.
In which case, we do tend to think of that as a walled garden solution. So there are many questions here, and there are many things that you might want to revise and think about.
Yeah, if a community like, I can have a congestion-specific draft for this. Yeah, because this I thought that without this framework, talking about congestion, no sense. Yeah.
Indeed. Yeah. So it's good to get started. It's good to hear what you've got to say. Are any of the ETSI documents available to the IETF to see? Would that?
Yeah,
is that possible?
in the ETSI, we every 3 months we have a conference just like this, but we have more detailed information, much longer presentation time than this. So there we have a lot of analysis for the problem and for even the political issue like the network neutrality, because this design target definitely consider that. Otherwise, service provider won't accept it. So I have a detailed analysis for that. And for this draft and all other works, definitely we will update for the ETSI.
Okay, please share that with the list, and please talk to the chairs later about how you wish to progress.
Yeah, thank you very much.
Thank you.
Okay, blue sheets. I got one of them here. Where is the other blue sheets? There were two. Who has not signed the blue sheets? Okay, all right. Okay, and this other one's been located in the back. Okay, so I think we're done at this point. Any other questions? Business, some things we got to deal with? Thank you all very much. I think we did find it. All right. Actually, I'm going to leave this thing, leave that thing sit here.
Yeah.
take progress.